Hi there, have you ever heard about the Joule-Thomson effect? Before that, here is our group members. The Joule-Thomson effect is the change of gas temperature when it undergoes isentropic expansion in an adiabatic condition. This effect was found from an experiment conducted by James Prescott Joule and William Thomson. This effect used to liquefy gas where a gas is repeatedly compressed and expanded, decreasing its temperature until the temperature drops so low that it condenses into a liquid. Liquid nitrogen and oxygen are commonly prepared that way on a vast industrial scale. However, a gas must be below its inversion temperature in order for the Joule-Thomson effect to work in the proper direction of decreasing temperature. For a better understanding of this effect, let us dive into the explanation of the Joule-Thomson effect. Imagine that we have two R-side of pistons separated by a porous barrier. This system is insulated so that the process will proceed under the adiabatic condition in which no heat is transferred from or to the surrounding. In the left side of the piston, the pressure is represented by P1, volume by V1 and temperature as T1. When the piston is pushed, the gas will flow through the porous barrier and the right side of the piston will expand. In the right-hand side, the pressure can be represented as P2, volume as V2 and temperature as T2. On the left side, work is done on the gas which contributes positively to the overall charge in energy. On the right side, the gas does work contributing negatively to overall charge in energy.
The total work done in this process is equal to work done on the left side plus the work done on the right side. The total work done on the left side is equal to P1 times 0 minus V1. This is because the piston on the left side initially has a volume of V1 and it decreases to 0 when the piston is pushed. Meanwhile, the work on the right side is equal to P2 times V2 minus 0. The initial volume of the piston on the right side is 0. As the gas expands, the final volume becomes V2. Adding these two total works equal to P1 V1 minus P2 V2. The change in internal energy is given as delta U equal to Q plus W. Since this is an adiabatic expansion, the heat energy Q will equal to 0. Thus, the delta U is equal to W. When we insert the above equation of total work done in the equation of the change in internal energy, we get that delta U equal to P1 V1 minus P2 V2. Delta U can also be represented as U2 minus U1. Thus, U2 minus U1 equal to P1 V1 minus P2 V2. Rearrange the equation, we get that U1 plus P1 V1 equal to U2 plus P2 V2. This equation is pretty familiar, right? Yes, it resembles the enthalpy formula in which enthalpy H is equal to U plus PV. Finally, from the equation, we conclude that H1 equal to H2. This equation proves that the Joule-Thomson effect occurs in an isenthalpic equation, meaning that the expansion occurs without a change in enthalpy.
Now, a question arises: how does this process relate to the change in temperature? As we already know, the mean kinetic energy of molecules in a gas is proportional to the temperature. It shows that reducing the average speed of the molecules is equivalent to cooling the gas. When a gas expands adiabatically without allowing any energy to enter from outside as heat, the average separation of the molecules increases. It is because the molecules move apart to fill the available volume in order to against the attraction of their neighbors. To reach greater separation, some of kinetic energy must be converted into potential energy. As a result, the molecules travel more slowly as their separation increases. This series of molecular events explain the Joule-Thomson effect for the cooling of a real gas.
Since we are familiar with JT effect, let's now take a look on JT inversion curve for a better understanding. These are the conditions of JT coefficients that correlates with temperature. This is JT isenthalpic curve. This blue region is cooling region where gas will be cooled. Meanwhile, this is region of heating where mu is less than 0. There are no cooling or heating process occurs at inversion temperature. Mu JT equals to 0. Next, the slope of Tp graph is equals to mu JT. Mu JT equals 0 for ideal gas means that the temperature of a perfect gas is unchanged by JT expansion. As the pressure drops, the temperature goes up and it will get hotter upon expansion. Based on this figure, nitrogen were easily to liquefied compared to hydrogen and helium since nitrogen have a higher inversion temperature. Gas must be below its inversion temperature in order for Joule-Thomson method to work. So the gases like helium and hydrogen with a low inversion temperature need to be cooled substantially before expansion of JT carried out.
For one industrial application, we choose petrochemical industry as an example. The cooling produced in the Joule-Thomson expansion has made it a very valuable tool in refrigeration. The effect is applied in the lens method in the petrochemical industry where the cooling effect is used to liquefy gases. The process is based on Joule-Thomson effect, which states when a gas under high pressure is allowed to expand adiabatically through a fine hole into a region of low pressure, it is accompanied by cooling. The term adiabatically means that apparatus is perfectly insulated, so no heat is lost to or gained from the surroundings. An obvious reason for the cooling is that when the gas expands from a region of high pressure to the region of low pressure, the intermolecular distance increases. Some work is to be done for increasing intermolecular distances. This is done on the cost of kinetic energy of the gas. Thus, the kinetic energy of the gas decreases and therefore the temperature falls. By looking at this example, in lens method, cooling is produced by free incident expansion of the compressed gas into a low pressure region through a small nozzle repeatedly. This ultimately they get liquefied. As you can see here in the diagram that the fresh air enters to the compressor where the gas is highly compressed at 200 atmosphere, then pass through the refrigerating liquid. The gas follows the pipes and comes out through a small nozzle to the expansion chamber. As you can see here, where the pressure of the expansion chamber is very low, that is what atmosphere and the gas get cooled. By repeating this process several times, a gas changes into the liquid state. This is the references that we refer to do this video. That's all from us. Thank you.